everyone. Good morning, everyone, and wish you a very happy new year. Hope everyone is doing well.
Good morning, Ramya, and Happy New Year.
Thank you. So let us all be very active in the session. Okay, not a only listening mode. Let us have a live session kind of. Please, question and answers are always welcome. Okay. Yeah. So I'm Ramya, the HR manager of Semicon Technolabs, and I welcome every one of you to this demo session on physical design. Semicon team is delighted to have you all here, and we are confident that you will be finding this session both informative as well as engaging. So, to be more engaged, I think we are expecting more responses from your side. It should not be just a one-sided thing, like where we will be talking and you will be in mute. Let us have it a very engaging session. So today we have in this session Mr. Kalyan Chakravarthy, currently working as a senior technical director for analog layout and circuit design team at Radiant Semiconductors. And also we have Taslim, the HR executive of Semicon Technolabs, who have been coordinating with every one of you for the registration process. And I can say a single point of contact for meeting all the training needs of Semicon Technolabs. So welcome everyone to this session. So before we dive into this session, I will just take a couple of minutes for introducing Semicon Technolabs. So Semicon Technolabs is founded in 2016 with its headquarters in Bangalore and also with established operations at Hyderabad. So I can say we are operating both in Bangalore as well as Hyderabad. And we are the leading providers of VLSI training and internship programs in physical design, analog layout, analog circuit design, design verification, and design for testability. So the current demo session is basically planned for starting the physical design training program in next 2 weeks. That's the reason for having this demo session. So all the trainings offered in Semicon Technolabs comes both in online and offline mode to accommodate various learning experiences or various learning preferences of the students. Usually the course duration for all these training programs will be varying between 3 to 6 months. And during this course period, you will be having in-depth understanding of the subject matter. And also you will be well prepared for reaching your career goals. We have a team of highly qualified instructors, each with more than 15 years of industry experience. All the trainers are selected very carefully to ensure that highest quality of training program, I mean, highest quality is ensured, and also they bring extensive expertise and knowledge to the table. So to go deeper into what we do actually, so Semicon Technolabs provide very flexible corporate training and internship programs in the fields such as DV, DFT, PD, and analog layout. To say for the current batch, I can say we are purely going in an offline mode. There's no online sessions for this current batch. And also to ensure a very good quality training to the students and also best outcomes then attain, we usually conduct module wise test to all the students, and also we conduct some mock interviews uh, after completing each module, and also we take some grant tests after completion of the half syllabus, and also after completion of the whole syllabus you will be having one more grant test, and also apart from this you will be having some soft skill training programs as well. This is where we stand apart from other training institutes, where all the trainers will be having industry experience, purely industry experience, and you will have one-on-one sessions kind of after completing your each level of tests, where you can clear all kind of your doubts. You can clear, I mean, we will be helping you to bridge all the gaps where you're lagging. And also we provide 100% placement assistance for all the trainees who will be taking training from us. Uh, I want to highlight and I want to just pinpoint here that it is a 100% placement assistance, not the 100% placement guaranteed. So it is like placement assistance means we'll be helping you to reach out to different uh, organizations who are actively hiring. We will be floating your resumes with these different organizations, and we will be giving you heads up about any kind of current needs in the market. So in the past 6 years, I mean, like 8 years of our establishment, we have a track record of over placing over 550 trainees in different product and service companies. Semicon Technolabs is affiliated, or I can say we are closely collaborated with many product companies and service companies for helping you to place in different uh, organizations. Okay, so this is about Semicon Technolabs. One minute. Oh, my slide is not moving. So yeah. So as you begin your career in semiconductor industry, it is very important for you to understand the incredible impact the sector has. So semiconductors are the backbone of modern technology, driving advancements in industries like electronics, automotive, and healthcare. So, for instance, the global supercapacitors market closely tied to semiconductors is growing rapidly from $2.05 billion in 2023 to a projected a value of $9.57 billion by 2032 with an impressive annual growth rate of 19%. This growth rate is always fueled by rising demand for the high performance chips in devices like smartphones and smart TVs, supporting technologies like artificial intelligence, uh, Internet of Things, and even the metaverse. These trends clearly highlight the exciting opportunities and the immense potential that lies ahead of for you in this dynamic and ever evolving industry. So I can say the semiconductor industry is growing, and there's always a lot of future as well as opportunities for the students who are trying to pursue their career in this particular field. So, coming to the eligibility criteria, like you all might be having the questions who can take this training programs with us. So, as I already told that we usually take internship programs as well as the training programs for students, right? So, all the internship programs or the duration for these internship programs will be varying between 15 days to 60 days based on the requirements of the students and based on the college needs. So these internship programs are for particularly for the students who are in their third year, second semester, or in their final years of BTech, or else for the MTech students, it could be in the third semester or something like that. But this demo session is particularly for the students who have already completed the BTech or MTech. Uh, so all the students who have completed their BE, BTech, ME, MTech, or in electronics and electrical engineering or related fields. So only the students who are from ECE, triple E, or the related fields, only these particular students are eligible for this course. And also they should have minimum academic aggregate of 60%. This is very particular because this will help for the placement assistance. As most of the organizations, either it's a service company or a product company, they look for the students who are having 60% of aggregate in their academics. Otherwise, most of these resumes who are having lesser than 60% aggregate will be screen rejected in many cases. That's the reason the eligibility criteria will be like 60 percentage in your academics, and you should be coming from either ECE or triple E background or some related fields. Okay, and coming to the course planner for this particular training program, as it's a industry training, it is for 3 to 4 months. The course duration will be for 3 to 4 months. Within this period, definitely it will be completed. And the sessions will be conducted purely offline from Hyderabad. So I'm stressing, though we are flexible, though we conduct both online and offline sessions, but for this current batch, this is purely offline from Hyderabad. And the students who want to join from Bangalore, they can be join, they can join from our Bangalore office. Like you will be having the live video conferencing sessions. Uh, okay, so it is purely offline this time from Hyderabad. but who want to join from Bangalore, as I mean, like whoever the residents from the Bangalore, if they don't want to move to Hyderabad for this training program, you can definitely join from our Bangalore office. You will be having the live video conferencing sessions. Okay, so all the students who are going to take this training program, you should be available whole day, I can say. Like you should be available from 10 a.m. to 6 a.m. So most probably the morning, the first half will be for the theoretical sessions, and the next half will be the lab sessions. So the working professionals and all that, if you want to join, you ensure that you will be making yourself available for whole day during this training sessions. So this is about the course planner. And coming to our corporate courses, like as I told you already, we are offering courses in ASIC design verification, design for testability, physical design, analog circuit design, and analog layout. And this demo session is now particularly for the physical design. So this is about the physical design whole course. As I have already mentioned, the whole course for this 4 months or 3 months duration will be divided into different modules. Uh, you can just check our website. You can quickly check our website. Um so hope. So this will be the syllabus for your, it is divided into different modules. This will be the syllabus for your training program. And during the, I mean, demo session given by the technical team, they'll be giving you more in-depth knowledge about these different modules. So coming to the EDA partners, like which tools we'll be using. For the current batch, the tools will be Cadence and Synopsys. So we'll be using these tools for giving you the in-depth, I mean, like tool experience and practical knowledge in the physical design. So what do our students say about Semicon? So in Google, we are 5-star rated, and you can see few of the reviews given by our students in Google. And coming to recent placement history, like we provide 100% placement assistance for all the students. We continuously work with recruitment teams of different organizations, and we'll be processing the student profiles to these organizations and help them placed in the different semiconductor or VLSI related companies. And also, what I can say, you might have a question regarding for how much duration we will be providing you the placement assistance. Our HR team is always in touch with all the trainees who are taking the training from us, who have already taken also. So they will be always, I mean, they maintain a database of all the students and constantly check who are being placed and who are not being placed. And they'll be floating their resumes to different recruiters and help them in the placement opportunities. So I can say we are there's no particular period what we can say, like only 6 months we will give the placement assistance or something like that. It's not like that. We'll be like until you are placed, we'll be helping you with the hiring process. So this is a quick history about our placement. So I think I have covered everything related to Semicon and how our training program will be going ahead. And if you have any further questions related to the training program, the training schedule, or fees or anything, you can reach out Taslim on this particular phone number. As I told, we are operating only offline. Our Hyderabad office is located in Madina Guda of Miapur, and our Bangalore office is at Marathalli Ring Road. So thank you, everyone. And before we start with the technical session by Mr. Casey, let me take a minute to introduce Mr. Casey. Mr. Casey is a technical director of analog layout circuit design team at Radiant Semiconductors. He is having around 18 years of experience, industry experience, pure industry experience. And earlier he worked with companies like AMD and Synopsys. I can say the recent company before joining with Radiant Semiconductors, that is AMD. So he is purely having 18 plus years of experience in physical design, analog layout, and analog circuit design. And his passion to teach and mentor the students is definitely the most value proposition and the reason why we have selected him as a trainer for this particular demo sessions. So Mr. Casey, along with his team members, technical team members, will be driving this training program, not only this demo session, and also along with his team, they will be driving the whole training program for the next 3-4 months. So tentatively, we will be starting this training program after Pongal, the post Pongal, that is like most probably from 20th of Jan, we'll be starting this training. So without any further delay, let us all welcome Mr. Casey to start with the demo.
Thank you,
Thank you,
Ramya.
everyone. Thank you. Yeah,
Thank
over to
you.
Casey.
Thank you, Ramya. Let me share my screen.
Excuse me, I have a small doubt.
Yeah,
Yeah,
please go
please.
ahead.
I'm from the CSC background, and someone also messaged that he is from BCom Computer Applications. Are we eligible for this course?
See, basically, I don't know how well versed you are with the digital electronics and all that. If you're confident and all that, it will be, I don't know whether you can catch it or not. And also, when it comes to the placement, the semiconductor industries will be specifically asking for ECE and EEE backgrounds or related backgrounds. That's the reason we give the eligibility criteria as ECE and EEE. But anyway, like the technical people might give a better answer because they know how you can catch up with these things or not. So going ahead in the demo might be Casey will be helping you with these answers.
Okay, thank you.
Yeah.
All right. Okay, so a warm welcome to everyone, and thank you for joining our PD demo. All right, so hope everyone are able to see my screen.
Yes, sir.
Yeah, it's visible.
Thank you. All right, so let me walk through the contents which we will be covering today as part of PD demo. When I say PD, it is nothing but physical design. Short form of physical design is PD. So first we will be covering an introduction to VLSI chip design, where we will be walking through what is electronics, right? Because in engineering stream, we have many different verticals, right? I mean, mechanical, civil, information technology, CSC, EEE, EC, right? And I mean, when it comes to VLSI and when it comes to physical design, right? I mean, we need to understand what is exactly electronics domain, and from electronics domain, how we move on to VLSI function, and from there, how we move on to physical design vertical, right? So we'll be covering, or we'll be walking through all of that in introduction to VLSI chip design, which is our first section in the technical side, right? And then we'll go to VLSI flow, which is our second topic, right? Where we will be understanding how an idea, a simple idea, right, of making a particular product, right? How that idea gets transformed into a finished chip, or I would say a finished working product, right? Which will replicate our idea, which we originally thought of. Okay, so what all steps it will go through, right? I mean, from the idea all the way to the product, right? I mean, what all different verticals we have in the journey of VLSI flow, right? We'll walk through that in the content number 2. Okay, and in content number 3, which is nothing but semiconductor manufacturing process, right? I mean, we'll just revise because folks who have studied VLSI as part of their 4th year, right? So it will be similar, but then we have captured the latest technologies that are being used in the manufacturing process, so that way we can come to know how from silicon. Okay, we have taken silicon as the example because that's the standard one which we are using since almost more than 2 decades. Even today, it is still trending, even though we have other substrates in line, right? But silicon substrate is still trending because of its advantages in terms of PPA, right? So we'll go through manufacturing process, how the sand is mapped into silicon substrate and how it is helping us to build advanced node chips, right? We'll go through that journey. Then fourth content is the main content, right? Where like we'll go, I would say deep dive, right? Because that is the whole agenda of this PD demo, right? We'll try to understand what is physical design in the entire VLSI flow chart or in the entire SOC flow chart, right? And then we'll try to go through the course content in detail again, right? I will just walk through the course content from the Semicon website as well, so that any questions or anything, right? We can take it up there, right? Of course, please do stop me if you have any kind of questions, okay? And I will be happy to share as much information as possible to make you understand or resolve the question, okay? So we'll go through the course content directly from our Semicon website, and then EDA tools. So we have Synopsys and Cadence EDA tools, right? And we'll go through the live EDA presentation. So I'll be showing you how the physical layout looks like. Okay, what all things generally we do in physical design, how the bird's eye view will be in terms of EDA tools. Of course, some of you mentioned you have worked on Cadence Virtuoso, Mentor graphics tools were there, and then MATLAB tools were there. But then here we are, here we'll go through the physical design related Synopsys and Cadence tools and what kind of projects we will be going through in the demo part. Okay, we'll be showing the exact projects which we'll be working on in the demo part. Okay. Right. And then finally, we'll spend some time, quality time on the question and answer any kind of questions you may have technically, right? And we'll be happy to share as much information as possible. And then, of course, finally, a summary note or a thank you note. Okay. So I will pause here for a minute or less than a minute. Anybody, any questions, you can raise your hand or you can unmute and then speak up as, if something is not clear in the content slide. We'll go slow, no hurry. We just need everyone to understand the demo part thoroughly and take home the technical content. Okay. Right. So let's go to first slide. Okay. In the contents. Introduction to VLSI, right? So before we go to VLSI, as I mentioned, first we need to recap or we need to understand what is electronic circuit design. Right, because again, VLSI is part of electronic circuit design only, right? So what does electronic circuit design mean? It is consisting of CPU, ROM, RAM, and any other glue logic. Okay, so we are aware like CPU, central processing unit, ROM, RAM, these are kind of memories which we use right in our day-to-day life as well, either in mobile or in laptop, any of the devices, right? We have all the three components, CPU, ROM, RAM. These are part and parcel of our any electronic product, right? Now, combinedly, right, if you have all these components along with glue logic, that is nothing but your electronic circuit. Okay, so it's the simple way of understanding the electronic circuit. Okay, electrical again is slightly different. Some of you mentioned you are having electrical background, AAA background. It's slightly different, not so much, slightly different, where we deal with bigger size electrical components. Okay, but electronics is something where it is a miniature. You can see on the right side on the finger, right? If you see the IC on the finger, it's so small, so small, right? So in the next slides, we'll see how small it is. It is it is very small compared to diameter of the hair as well. Okay, in the next slides, we have that data captured. Okay, so electronics is mainly like a very small circuit, very, very small circuit, okay, in terms of size, not in terms of complexity, in terms of size, which does many functions. Many functions, you name it, and I mean, pretty much now for everything we have electronic circuits. Everything. I mean, very rarely we see that. I mean, there is no such electronic gadget available. Okay. Now, electronic circuits, right? VLSI lets IC designers add all of these into one chip. Now, for electronic circuit, we need CPU, ROM, RAM, glue logic, everything to be put inside one single case. Okay, so that part is taken care by VLSI. That's how VLSI is interlinked to electronic circuits. Okay, so VLSI began in 1980s, right, when complex semiconductor technology was being developed for integrating transistors. Now, if VLSI has to help electronic circuits in order to get all these components into one chip, okay, how did the journey of VLSI start? So it all started, I mean, way back in 1980s, right, where the evolvement of transistors came and which helped, right, in order to integrate these transistors into a single chip. Thereby, you have an electronic circuit inside a single chip. Okay, and this evolution came because of improvement in the semiconductor technology. Because directly transistor cannot come, right? I mean, if we go one step back, it is nothing but semiconductor technology. Semiconductor technology is the one which evolved somewhere around 1980s, right? And that helped VLSI vertical to integrate many and many transistors into a single chip. Okay, now let's go a step back and understand, did directly VLSI come into picture? No, right? I mean, we have several milestones. We had several milestones which we crossed, and now finally we ended up with VLSI. I would say we have ULSI as well, right? But then in common, in general, in the market, we still refer to VLSI. Okay, so previously, VLSI was a successor to LSI, which is nothing but large scale integration, medium scale integration, and small scale integration. We had three generations of transistor integration happened post that VLSI came, and then VLSI also has crossed, and it is ULSI. Okay, so let's define what is VLSI. Okay, VLSI, which is nothing but very large scale integration, is the cutting edge process of crafting integrated circuits by integrating thousands, millions, or even billions of transistors onto a single silicon chip. Okay, these ICs power everything from everyday gadgets to state-of-art supercomputers. So VLSI design involves working with circuits at incredibly small scales to create high performance and compact electronics. Okay, so overall, in a nutshell, if we have to say, VLSI is a technology which will help to integrate billions of transistors into a single chip so that you can have an electronic circuit existing in a chip. Okay, that's how we can connect the dots. Okay, please pause me if you have any questions, if you have any inputs as well, not just questions, any inputs as well. All right. Now, as I mentioned, VLSI came into existence somewhere in 1980s. Okay, and that too because of evolvement in the semiconductor technology. Now, how can semiconductor technology evolve? Only when the transistor technology evolves. These two are interlinked, right? Now, on the left side, if you see, right, so left side, the first image which you can see here, that is nothing but a transistor. Okay, a single transistor was so big. Okay, 1940 transistors invented in Bell Laboratory. Okay, the left side image, it was so big transistor. Okay, 1950 first IC JK flip-flop by Jack Kilby at TI. Okay, from transistors, by integrating the transistors, right, we started preparing the integrated circuits IC. Okay, then 1960, early 60s, small scale integration SSI, 10 transistors on a chip. Let me take the laser, that will be helpful. All right. So in 1960s, right, if you see SSI, only 10 transistors on a chip. Hardly 10, because the size of transistor was so big. On the left side image or in the middle image or in the right side image, you can see how big the transistor is. So we cannot integrate multiple transistors onto a single chip in order to get a electronic circuit implemented in the chip. Okay, so in SSI era, only 10 transistors. Now in MSI era, medium scale integration, hundreds of transistors. Okay, then in LSI era, which was in early 70s, thousands of transistors. That's it. Now VLSI came into picture in early 80s, right? I mean, where like 10K of transistors, right? Later it increased, and then in 1989 it became Ultra LSI. Okay, but still even today we refer it as VLSI, but advancement has happened so much because of the shrink in the transistor size. This is again thanks to semiconductor industry, where like semiconductor veterans, they helped in order to improvise the process of semiconductor so that the transistor size can be decreased and more transistors can be accommodated within a single integrated circuit so that a bigger electronic circuit can be put inside a single chip. Okay, all right, any questions so far? All right, let's move on to the history of VLSI. As I was telling in the first slide, right? I mean, the size of the transistor is so small, right? I mean, compared to the diameter of the hair, right? This is just in 16 nanometer, and right now we are working in less than 2 nanometer. You can just imagine how small the transistor size will be. Okay, the journey of VLSI design began in 1950s. Okay, this is again related to LSI, MSI, SSI, right? With the invention of the first transistor. This breakthrough was followed in 1960s by the development of first integrated circuit, a milestone that transformed the electronics industry. The advent of IC significantly shrank the size of electronic devices while vastly enhancing their capabilities. Okay, and then 70s, as we know, I mean, we had LSI, and then 80s we have VLSI, right? In 1983, okay, VLSI design emerged as a specialized field with the first VLSI chip being designed in 1983. Okay, since then the field has rapidly advanced, pushing the boundaries of chip complexity and efficiency. Okay, any questions? Are you guys able to catch up with these slides? Can someone confirm? All right, I can see uh, hands up by Deepak. All right.
Yes, sir.
All right, yeah. So we have two images on the top, right? One is 128 MB, another is 128 GB, right? I mean, these are just the regular memory cards, okay? Memory cards which we use in our day-to-day life, right? I mean, for memory extension, right? Now, 128 MB has been mapped into 128 GB. What is the reason? The reason is the size of transistors have come down. More and more transistors can be incorporated in the same size or a lesser size of the chip, which was there earlier, right? Now that has been captured here. MB has become GB, and you can also see that the size has slightly shrunk. Okay, this is nothing but Moore's law. Okay, Moore was one of the ex-employee of Intel, which is a very big company in semiconductor industry. Okay, so Moore's law is the observation that over the history of computing hardware, the number of transistors on integrated circuits doubles approximately every 2 years, 18 months. Okay, so as you can see here, right, I mean, from the Moore's law, right, up till 2030, right, number of transistors that can be put inside a single chip that keeps on doubling every 18 months, which means the size of the transistor has to come down, which means the semiconductor process has to keep on advancing so that it can reduce the transistor size. However, again, there should not be any compromise on the functionality of the transistor, right? So without compromising on the existing metrics, the size of the transistor has to come down. And of course, along with that, even the power consumption has to come down and performance has to increase, right? So this is called as Moore's law. So please stop me if you have any questions. Okay. All right. Anybody had any question? Okay. All right. Now, as you can see on the first image, right? I mean, this is something called as wafer. Okay. The foundry person is holding the wafer, right? I mean, this is a very big wafer containing tiny rectangles. Okay. These tiny rectangles are called as chips. Okay. Now, what we have to do is in physical design, which is our demo for today, right? We generate the layout. This layout will be mapped into these tiny rectangles, which we see here. Okay, this is nothing but your integrated circuit. Okay. Now, this layout, once it is mapped into these tiny rectangles, right, it has to be fabricated in order to get you the die, which you can physically see. Physically, you can hold it. Okay, of course, after packaging, right, not before packaging, because the EST that is present in our hand, right, it can damage the die, right? Now, you might have used breadboards, right? I mean, how many of you have used breadboards during your labs? Breadboards, and then we have ICs, right? I mean, these ICs will be having the pins. These pins will be hooked up onto breadboard, and then we use the breadboard to connect, right? We have wires to connect from one IC to another IC as per the circuit given in the lab. Have any of you done that in your labs? Maybe in third year
Yes, sir.
or you have done it, right? Okay. So you can correlate, I mean, the scenario here, which is reflected in this slide. All right. And of course, we call this as bond wire, the wire which connects from IC to the bond pad, that is pins, and then these are the bond pads. Okay.
Like 754 IC we have used. Like there are different types of IC, right?
Right. Exactly. And you have the electronic circuit in your lab manual, which you have to replicate in the labs using this
Yeah,
bread.
we have to perform like a half adder or full adder.
Correct.
Like those kind of circuits we have to implement by using resistor capacitors and some kind of network also we will use, right? Network theory, like designing
Exactly
a
right.
full wave, half wave
Mm.
rectifier, full wave rectifier.
Mm.
Like this kind of circuits also we will design.
Exactly right. 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 Yes. All right. Let me go to next slide. Okay. These are all the different products. Okay. Which we use in our day-to-day life, right? You can call it as like end products of electronic devices, right? So we have so many things in place, all the way from laptop to mobile phone, right? Laptop, mobile phone, camera, everywhere, video games, everywhere we have VLSI in place, right? And then helping out the electronic industry to boom further, right? And these will contain different things. For example, processors will be there, right? CPU, DSP, controllers, then memory chips will be there. These will be common. These two things will be pretty much common across all the majority electronic products. Then analog will be there for mobile communication, right? Because we don't want to miss out any kind of data. So continuous signal will be there. Then programmable, sometimes instead of SOC or ASIC, we go with FPGA. Of course, SOC, ASIC, and FPGA, these are the three different type of ICs which we have in the industry. Okay, then embedded systems, right? I mean, used in cars, factories. Embedded system is nothing but you place the chip onto a board. That entire board will be part of embedded system along with C programming, right? And then system on chip, right, where everything on the board, what all components you have. For example, oscillators you have, let's say resistors you have, capacitors you have, everything. If you put it into same chip, inside the same chip, that is called a system on chip. Okay. Amazingly, the original Bell Lab invention of the transistor, combined a decade later with refining implementation of an IC, continues to drive exponential economic gain, right? When you have so many products in place, so much of market is there for electronic goods, okay, automatically your economic gain will improve in the form of both improved productivity and growth of new applications. Today, an integrated circuit can perform almost any electronic function on a piece of silicon less than a centimeter square. You can just imagine. Okay, from a PC to a cell phone to a television to an internet router, the industry can conceive, design, and deliver that function into an extraordinarily cost-effective and convenient form, a single silicon IC. Okay, that is nothing but your SOC. Everything you can put it into single SOC, just plug and play. That's it. Okay, so that's how the advancement is. Right? Mass integrated circuits. Okay, so 1970s processors usually had only NMOS transistor. Now we have PMOS as well, right? Initially we began the transistor technology only with NMOS, right? And gradually, because of disadvantages in the NMOS, because it was expensive, consumes more power when idle, right? So that's where industry had to evolve with PMOS as well. Okay, PMOS means P-type transistor, NMOS means N-type transistor. That's how we have CMOS process in place, which has both N-type transistor, which is NMOS, and P-type transistor, which is PMOS. Okay, so 1980s to present till date, 2024 or 2025. Okay, CMOS processes for low idle power. We depend on the CMOS. Majority products are still using CMOS till at least till 5 nanometer or 4 nanometer, right? And gradually we are moving to FinFETs. Okay, so this is how the chips were looking. Okay, and this is how the generalized standard cell will be. So we have VDD and VSS, and then we have P-type transistor and N-type transistor. Both are separated by the diffusion spacing. All right. Now let's see the first computer. Okay, this should be an interesting slide because if you can see here, the size of the first computer is so big. Okay, this is in 1832, almost 90 plus years back. Okay, the baggage difference engine. This was having 25,000 parts and the cost was pound 17,470. Okay, so it was so big and it was mainly based out of mechanical operation. Okay. So this will be clear in this particular slide. If you see here, we have 1, 2, 3, 4. 4 people are working. Okay. The first electronic computer, 1946. Okay. This computer was in 1832. This had majority mechanical parts. This is purely electronic computer in 1946. But then a single computer was the size of a big room, big hall, right? And then almost 4 people or maybe more, they were manually helping to operate this computer. Okay, that was the situation in 1946. Okay, the first generation of modern electronics is thought to have begun in 1942 with the invention of electronic switches and miniature vacuum tubes. By 1946, a large-scale computing device based on these new inventions was developed. The computing device was known as Electronic Numerical Integration and Calculation. This is the full form of ENIAC. Okay. ENIAC could perform thousands of calculations per second and was used in many applications such as scientific research and weather predictions. Okay. So this is how the industry evolved actually. These are some examples. Okay, all the way from right side 0.25 micron, 3.5 micron, 0.6, 0.8, 1 micron, 1.5 micron, right? Now, as you can see here, the size is keep on reducing. Okay, this is because of advancement in the semiconductor process, which helped in advancement of technology process. Okay, when I say technology process, the size of the transistor has come down, right? Mainly area point of view, clearly you can see the difference. The size has come down for the transistor so that many transistors can be incorporated into single IC to form an electronic circuit. Okay, manufacturing node technology at a particular channel length. Okay, this is mainly because of the advancement in the technology nodes. Okay, technology node is nothing but transistor channel length. Correct. Deep submicron technology 250 nanometer to 100 nanometer, nanometer technology 100 nanometer and below. Okay. These are some examples, right? I mean, previous examples where Intel was using all these technology nodes and how clearly you can differentiate the reduction in the size. Okay. Now FinFETs. So we went through a recap of CMOS, how CMOS came into picture because initially NMOS was there. There was no PMOS, but because of NMOS being expensive and then power consumption of NMOS during ideal state was more, that's where like PMOS came into picture. And in PMOS, right, I mean, we were able to mitigate the disadvantages of NMOS. So NMOS plus PMOS combined, it gave into new technology called CMOS. And CMOS, we are even, using it even till today. Okay, till 5 nanometer, till 4 nanometer technology node, we are using CMOS. Okay, beyond 4 nanometer, let's say we are going to 3 nanometer, 2 nanometer, right? There, FinFETs, we are trying to map our transistors to FinFETs. Okay, now what is the advantage of FinFETs, right? Now the advantage of FinFETs is, as you can see, dynamic power and leakage power, right? So dynamic power, which is nothing but when the transistor is switching, we call it as dynamic power. The power consumption during switching operation, that is called as dynamic power. Leakage power, when the transistor is not switching, when it is on but idle, that is called as leakage power. Okay. Now both dynamic power and leakage power are very, very less in FinFETs as compared to planar MOSFET. Okay, planar MOSFET is nothing but your CMOS. Okay, because of advantage of this power consumption, because we need our power consumption to be reduced as small as possible, right? The reason being majority of the electronic circuits are battery operated, DC voltage supply, battery operated. When you are running electronic circuit on a battery, right, I mean automatically we need lesser power consumption for an IC so that the battery life will increase. That's the reason, I mean, we have moved into FinFETs, right? Okay. And then if you see the above image, planar MOSFET, which is nothing but your CMOS, and then a 3D FinFET, right? Now these fins are there. Additionally, you have fins to the source, you have fins to the drain, right? This is FinFET if you take the 3D image. But then in planar MOSFET, you don't have the fins, right? I mean directly you have the source and drain, okay? And in between, in both the cases, you have gate. Okay, this is how on a very top level in the 3D view, you can clearly see the difference between planar MOSFET, which is nothing but CMOS, and 3D FinFET, okay, which is being used in the very latest technology nodes, 4 nanometer and below. Okay. All right. Any questions so far? All good? Is it understandable?
Yes, sir.
All right. Yeah. Thank you. Let's go to next slide. Okay, here we have given a very top level bird's eye view on different processes. Okay, so we focused mainly on CMOS, right? And then next we focused on FinFET. But apart from CMOS and FinFET, we also have different processes. Okay, so bipolar CMOS, DMOS, okay, silicon on insulator, gallium nitride, silicon carbide. Okay, these are all different other processes being experimented. Okay, these are not actually into projects, okay, but they are getting experimented, right? And the material which is being used for these processes is different. Okay, for example, in gallium nitride, the material used is gallium nitride, and in silicon carbide, it is silicon carbide, SiC and GaN. Okay, so this makes a difference. And then if you see CMOS, BCD and SOI, though the material is same, the technology type is different. Okay, so it is planar bulk for CMOS, whereas for BCD it is bipolar CMOS and DMOS, whereas for SOI the technology type is silicon on insulator. Okay, now different advantages, applications, disadvantages has been discussed here. Okay, but overall when we see, right, I mean CMOS and FinFET, these are the two main things which we have in industry right now. Okay, the other things I would say, probably as per the Moore's law, till 2030, every size of an IC, right, the number of transistors that needs to be placed in the IC will keep doubling every 18 months, right? Once we touch the end of the tunnel, right, probably by 2030, that's where like we need to be prepared, right? Because their CMOS and FinFET might not be helpful for us to integrate more and more transistors and to meet the criteria of Moore's law. Probably that time we need other processes like BCD, SOI, GaN, SiC to help us out in order to keep the VLSI industry and electronic industry moving forward and to create the miniature chips. Okay, what we need. All right. So I'll just touch base on this CMOS. Okay, CMOS key applications, microprocessors, digital ICs, memory, analog circuits, and then for FinFETs, it is high performance CPUs, GPUs, low power electronics. Okay.
Sir, I think other than CMOS and FinFET, while we are using different processor now, it will create like there is an disadvantage like there is a different limitations for the device and it won't work like up to high temperature. For CMOS and FinFET, they will use like a high temperature and low temperature, but compared to other components, they won't helpful for like different kind of temperature and the device will get failure.
Correct. You are right. You are right. So technically we call it as yield, right? I mean,
Yeah.
when we do fabrication, finally the chip, right? I mean, the finished chip, packaged chip, it has to work in the product. So yield is something where the die that is coming out of the fabrication, I mean, the die is not working as per expectation. Maybe partially it is working, or only in few scenarios it is working, but not completely as per the expectation, right? As you rightly mentioned, I mean, it may not be working in one particular temperature zone. It may not be working in one particular supply voltage, right? Still the
Yeah.
work, I mean, it's like work in progress, right? But
And
then,
but
mm,
researchers were like implementing different components, and they were seeing their like what their variations, and they are just measuring at like doing researcher purpose. They are collecting the information. That's all,
correct,
and they're
correct,
fabricating the device.
correct. You are right. You are right. So these are all in R&D phase, right? I would say are like being used in less critical chips, right? To understand how the behavior of the process is, or how the behavior of the material is. Mainly, it all depends upon the material and the technology type. Okay, which material we are using and what is the technology type we are using, right? These are all in case at a certain stage where we say that, I mean, CMOS has reached a limit, right? Or let's say FinFET has reached a limit, right? We need to have plan B as well, right? I mean, what else? I mean, how can we take the industry forward, right? So that's where like these new technology types or these new materials are being used, and industry R&D team, right? I mean, they are working hard in order to understand the characteristics of these materials, and how they can eventually replace CMOS and FinFETs, right? Down the line, I mean, not now, but maybe another 2 decades later, right? So and based on the need, based on the different applications, it's not just about I mean, one side, like we are checking on the yield point of view, but then on the other side, even the demand for electronic devices from the customers is so huge. Every day we have one or the other electronic gadget coming into market, right? And to meet those requirements as well, we need to keep ourselves updated with the latest processes and the technology type that can be used into for manufacturing these devices, right? Yeah. So you rightly mentioned. I mean, these are still in the validation phase to meet the future demands.
Yes, sir. And
Yeah.
they will do research because of their characteristics purpose, like
Mm.
results. They want to see better results, and according to that, they in future, if there any case, if silicon is not available in future, then they will go to this kind of processor maybe.
Correct. Correct. That's true. That's true. That's true. Yeah. And as we know, I mean, silicon, right? I mean, if you see both the things, right? CMOS and FinFET, silicon. So silicon is also scarce to find. I mean, especially the quality silicon which we use for IC, right? I mean, we also need to look into how abundant the silicon is, or what is the costing of silicon, right? I mean, because silicon chips are usually costly, expensive, right? We need to find cost-effective material as well, which we can use it for our fabrication point of view. So multiple things go into play here, or multiple elements fit into the equation of which process is best for us, right?
Actually, sir, the thing is that silicon is available everywhere. So, and it is easy to fabricate, and it is easy to do experiment upon silicon. So that's the reason why they use the silicon material. And when we see like gallium and those kind of metals, it's not easily available. So we won't go for that.
A slight correction. So silicon is also scarce, right? I mean, because so many chips are getting fabricated. So quality silicon is definitely a shortage, right? And yeah, maybe can we take this park this question now, and can we take it up in the manufacturing process? Would it be fine?
Yes, sir.
Yeah.
For
So
manufacturing, it's fine.
right. So in the
Because
manufacturing
for
process,
silicon, sir, actually, the thing is that silicon has a good characteristics compared to other elements. So we
correct,
will
correct, correct.
prefer mainly silicon itself.
Right.
And whatever, if you compare those things like silicon and other materials, other elements, um, there is it has good advantage of silicon and compared to other elements. So
Correct.
silicon is more suitable material to fabricate.
Correct. Exactly. And the biggest advantage, as you can see here, is low power consumption. It is cost effective and high density integration. So a lot of transistors can be comfortably integrated in the CMOS logic. Right? I mean, there are several key advantages here. Okay. All right. It was a nice discussion. Yeah. So we'll park this question now, right? And then we'll again reopen this question, revisit this question during the semiconductor manufacturing process segment. Okay. All right. So let's move on. So these are all different VLSI companies, okay, which we have been working on, which the industry is working on. Okay, lot of companies all the way. I mean, some are noted companies. For example, let's take IBM, right? I mean, IBM is more than 100 years old company, right? Wipro, we know. Tata Elxsi, we know. I mean, these are all well-known companies, right? Then National Semiconductors. Earlier, we used to get TVs, right? TVs manufactured from National Semiconductors. Probably in 1990s, early 2000, we used to get TVs from National Semiconductor. And then Texas Instruments is again a well-known company. AMD, right? We have AMD again. I mean, it started its operation somewhere in 1960s. Okay. Then what else? Connexent is also again a well-known company. Motorola, I mean, pretty much I think everyone knows about Motorola because in one era it was dominating the mobile industry. Many mobiles were from Motorola, right? So many companies, right? I mean, to name a few, I mean, we have picked up few companies, but then there are a lot of companies working in VLSI field. Okay, and thanks to advancement in technology, because of which, I mean, it has enabled VLSI industry to grow, right? So it's ever evolving industry, I would say. All right. So I have just put across cost metrics, okay, just to give a feel on how VLSI industry uh, economics is managed. Okay. Now, when you look at the EDA tools, okay, so EDA tools is something electronic design automation tools. These are tools which are used for designing your chip, for generating the layout of your chip. Okay, as you can see here, as the technology node is becoming smaller and smaller, okay, the cost of EDA tool is getting increased. These are all in $1 million. So for 5 nanometer, it is something around $250 million. The cost is getting increased day by day. Okay, right? Because so many transistors, so much of logic, so much of functionality has to be incorporated within the same IC. Now, hardware design cost. Okay, so based on the technology node again, right? I mean, see verification, physical design, logical design, photo mask. Okay, if you look into the physical design perspective, right? The orange color, right? So this kept on increasing. For example, from 250 nanometer to 180, 130, 90, 65. Okay, in 65, this orange color, right? You can see here it is on a higher side compared to all the rest of the technology nodes which are there in this snippet. Okay, because it's not so easy to design physical design, implement the layout, right, which is meeting the requirements of the design, meeting the requirements of the fabrication. Um, so many criteria has to be met before we can fully say the physical design layout is ready to pass it on to a foundry, right? So that's where even the physical design cost also has increased as the technology node got smaller and smaller. Okay, non-recurring cost, NRE is something non-recurring cost where like we NRE cost breakdown of ASICs. Okay, now if you see production, foundry NRE, design NRE, right? Usually why we call it as NRE, the reason being initially we have to pump in the money in order to make a product. Only when the product is finished and then it is sold to customers, right? Then we start recovering the money, right? So now NRE is a word which is used where initially we have to pump in the money without expecting the profits, right? Only when the product is entered into market, then we can start recovering the money. So it's something called non-recurring engineering cost. Okay, this also has increased. Okay, over the span of years, right, as the technology node got smaller and smaller. Okay. Now let's see estimated wafer price per node. Okay, this is again related to fabrication. Okay, these are just general ideas to make you aware how the technology is improving, how much of money is rotating in VLSI industry. Okay, so 90 nanometer all the way to 2 nanometer, right? In 2 nanometer, if you see, right, I mean the blue color chart, right? It has dominated all the other technology nodes, 3 nanometer, 5, 7, 10, and all, right? It is in USD, right? So the cost of fabrication is also very high because it's not so easy to fabricate very, very tiny transistors, right? Because as the technology node becomes smaller and smaller, the size of the transistor becomes smaller and smaller. And it's not an easy job for fabrication person to fabricate those tiny ICs within a small boxes which we saw earlier in the wafer. A person was holding the wafer, right? So within those small boxes, you need to have these transistors incorporated into those small boxes so that finally you have chip or you have die. Okay. All right. So global semiconductor capacity increase by location. Okay. So let's look at the graph. Okay, 2012 to 2022 versus 2022 to 2032. Right. So as you can see, China, right? I mean, China is dominating in the VLSA segment, right? And then, right? I mean, US, Europe, Japan, South Korea, Taiwan, and others, right? I mean, they are sharing the business. Okay, but majorly the business is coming from China, and of course, right? I mean, India is also evolving, which we have captured in the second slide, thanks to Narendra Modi ji and all the government officials who are involved in the semiconductor industry, right? For increasing the semiconductor opportunities in VLSI, which is covered in the next slide, right? As you can see here, okay, almost majority of North India, right? I mean, as you can see here, right? Gujarat, Maharashtra, Assam, again, different plants in Gujarat, Rajasthan. Lot of money has been invested here, few in billions, few in millions. Okay, and the main intent here is we should be able to have our own fabrication unit. Okay, we should be able to manufacture the complete chip at our end, made in India, right? From idea to the finished product, everything has to be done in India. That's where the Indian government mission is. Okay, semiconductor manufacturing projects in India. This is the latest one taken in 2024, right? Based on the multiple events where our Prime Minister inaugurated, right? I mean, all these different verticals. Okay, India Semiconductor Mission. All right. And multiple companies are also lined up here. For example, if you see Tata is well-known company, right? They have invested the money, right? How much? It's like $11 billion. Okay. And on a similar note, like we have Micron, Renesas, Stars Microelectronics, Adani Group, Adani Tower Semiconductor, and then Tata Electronics. Okay. So India is also competing in order to beat the market and have end-to-end product development done in India, okay, without depending on other countries. Okay, so what does it indicate? It indicates more and more job opportunities within India in the coming years. Okay, that's the take here. And then let's look at semiconductor companies ranked by market cap. Okay, these are all the different companies. And then you can see NVIDIA has touched a trillion, not even billion, trillion. Okay, so this is how the revenues are in terms of VLSA companies, and then followed by TSMC, Broadcom, ASML, AMD, Qualcomm, all the way till Marvell. Okay. Of course, these are all different VLSA foundries, right? I mean, the most famous being TSMC, and then Global Foundries, Tower Semiconductor. These are all different foundries, right, which provide us the die, which we can use it for sending to market post packaging. Okay, and EDA companies, majority EDA companies are still limited. I mean, we have Cadence, Mentor, and Synopsys. And in our demo, we'll be connected either with Synopsys or with Cadence, right, in order to provide the demo related EDA tools. Okay. Now let's go through the VLSI design challenges. Okay, this is another segment, right, where we are discussing on the VLSI design flow, on how the idea can be mapped into a finished product. Okay, so goal, designing circuits with increasing complexity is in always shorter times. This is always the goal. Even today, the schedule is a challenge. Okay, so computer has to take over routine work and deliberate the designer from unnecessary low qualification work, shift of design activities to higher level abstract work, right? And computer has to support new design methods. We need to take care of artificial intelligence and machine learning technologies as an advantage for us in order to reduce the schedule, right, and to deliver the chip to market as soon as possible. Okay, time to market. There is always a stronger market pressure. Okay, decreasing design window, less tolerance for design revisions. Okay, which means less tolerance for design mistakes. Okay, so we cannot tolerate the mistakes. We cannot have a big design window. Okay, there is always a stronger market pressure for time to market. This is again a technical term where like time to market means in how much of time the idea can be mapped into a finished chip. Okay, exponentially more complex, greater design risk, greater variety, and a smaller design window. Okay, what does it take to design VLSI system? Right, all the way from idea, we need to write it down into specification, technical specification. Then it has to be mapped into design system. From there, we need to analyze and model the system. That's where you have these MATLABs and all those things, right? And from there, right, if satisfied, then we go for fabrication. That's where, like in the previous slide, we saw like so many fabrication units are there: TSMC, Global Foundries, Tower Semiconductors, right? And then finally, once the die is ready, we have to test it. And if everything is working fine, we go for sending it or releasing it to market. Okay. All right. So application or idea, right? Any idea, whether you want to design a medical application chip or an automobile chip or a aero industry related chip or a biomedical chip, right? Consumer chip, right? Industrial application chip. So many applications are there. First, we have to have a clarity as which application and what idea to serve which application, right? I mean, we should have clarity in the idea and application for which we are designing the chip. Okay. Once we are clear, we have to map that into specifications, right? It can be in the format of instruction set, interface, organization of the system, functionality of each unit in the system, and how to communicate into other units. Okay. Once it is mapped into specification, then design and analysis, right? I mean, we have the design ready. That design, I mean, like it's similar. I mean, Verilog and VHDL, right? That has to be mapped into layout, and then we have to do the routing, and then finally mask layout patterns. Okay, so this comes in the fabrication part. Okay, and this comes in the physical design part. Okay, then fabrication, right? I mean, mask layout patterns, it is going for tape out, and then the fabrication person will be mapping that into die, right? I mean, the same wafer image where we saw that each of the rectangles have the electronic circuits. Okay, right? And then this is the packaging which has to be done, because with bare hand we cannot touch the die, because ASD will be discharged from the bare hands to the die, which can damage the die. So that's where like we need bond pad, bond wire, and pins to be present so that we can actually touch the uh, chip, and then we can integrate into the product without the fear of ESD. All right, and then finally we have the die and finished chip, test and packaged. This finished one will go to market. Okay, it can be sold as an individual chip, or it can be put into a product and we can sell the product as well. Either way. Okay, evaluate design and compare to model. This is where your MATLAB comes into picture again, where we evaluate the product. We check the signal integrity, power consumption, input output behavior. Does the chip function as it is supposed to be? Does it work at desired clock frequency? Okay, all these things matter a lot, and this is the PCB board. Okay, if you open any electronic device, right, you can easily see the electronic board sitting here, and then we have chips integrated here. Okay, these are all the chips, multiple chips which are working together, right, which are connected through routes in the board. Okay, we do this soldering here in order to connect all these components. Okay, and then different VLSI styles are there. Okay, digital and analog, right? And then again in digital we have memory related and logic related. Again in logic we have ASIC, FPGA, SOCs, right? Now mainly physical design, right? I mean we'll be concentrating on the digital side where we can implement either the ASIC, we can implement either the SOC. Nowadays we are even using physical design for implementing the FPGAs as well. Okay, and combination of analog and digital, that is called as analog mixed signal IPs. Okay, where like we have analog and digital both within a same SoC, right? So here as well we can use physical design. So everywhere any kind of chip which we are manufacturing, which we are planning to design, physical design will be there. Okay, so full custom application specific integrated circuit, which is ASIC, programmable logic, which is PLD, programmable logic design, and FPGA, system on chip. FPGA means field programmable gate array. Okay, so these are all different VLSI design styles which we choose for our project. Okay, based on the requirement. Now, semiconductor value chain, right? I mean, we have design, right? These are the design companies, integrated device manufacturers, which means they have their own fab as well. That's the reason we call them as IDMs. Intel has one fab, Samsung has one fab, right? And these are the EDA tools which we use in order to do the implementation. These are the IPs, ARM IP, Synopsys IP, Cadence IP. And these are fabless companies. I mean, AMD does the design, but they don't have fabrication unit. They have to depend on the fabs to get the fabrication done. Okay, that's where the fabs will come into picture. And for the fabs, they need some equipments to manufacture the chip. Okay, for a particular technology node. Those equipments will be coming from these companies, wafer fab equipment. Okay, finally, once the die is ready, then we send it to packaging. Okay, and for testing the products in the fab, okay, these companies will support WFE or semi-cap companies. Okay, now once the packaging is done, okay, these packaged chips will be sent to different companies. It can be Apple, it can be Intel, AMD, Nvidia, memory related or analog related or ASIC related. Okay, and finally it will be sent into market. Okay, this is how the value chain looks like. Okay, so many companies, so many people, so many activities have to go in place in order to get the final chip. Okay, right? And a similar kind, okay, the fabless model where they don't have the fab of their own, they have to depend on other fabs, right? The supplier layer where we do the manufacturing, okay, and the integrated model, right, where the companies have their own fabrication unit. They don't depend on the external fabrication unit. That's how the three broadly differentiated models are there, okay, in the semiconductor value chain. And then embedded systems. Okay, embedded systems, again, we have program memory, data memory, right? As we can see in our laptop or mobile phones, right? Any iPads, right? Different program memories are there, different data memories are there. Under data memory, we have DRAM, EEPROM, SRAM, okay? And under program memory, we have flash and ROM, NVROM, NOR, NAND, okay? So memory types also have to advance. Okay, you remember, I mean, in the very beginning, I showed a finger where like 128 MB was there a couple of years back, and then it has become 128 GB. The reason being advancement in the embedded systems memory types. Okay, because of this advancement only it was possible. Okay, and this is packaging, right? I mean, the black color one which you see here, right? I mean, and the leads which you see here, this is all packaging, right? How the packaging evolved in order to encapsulate the die within it. Okay, 1970s to 80s to 1990s and 2000, 2010, right? You can see so much of advancement. Here it was a single IC, right? And here you can see multiple chips are sitting within the same IC. Multiple chips, and here you can see below one layer of chips and above another layer of chips. This is called as 3D, this is called as 2.5D. The packaging industry has also evolved so much that multiple chips can be put inside a single package, which was not possible earlier, couple of decades back, but now it is possible. Every industry is evolving. So we were discussing about packaging, okay, how packaging industry has evolved all the way from very beginning, right? Very beginning stage where like we had only one single chip sitting inside a package to all the way till multiple chips sitting in a package. And then we have again different layers of chips being sit into a package. I mean, kind of an apartment where like on the top layer we have multiple chips, and on the below layer we have again multiple chips sitting in. Okay. So the complexity of packaging also has evolved where they can absorb more and more chips into a single package. Okay. We were talking about intellectual property pre-designed components, okay, which we can procure from the vendors directly in order to reduce the time to market, because we always have market pressure. As we discussed previously, right, in the VLSI design flow, market pressure will always be there, where like in a lesser period of time, in less schedule, we have to get the chip ready. Okay, that's where your IP will come into picture, handy to procure it from the vendors. Okay, because these are pre-designed components. Okay, it saves time,
Sir, I
design
think it
cost.
reduce. Sir, I think it reduces the complexity too,
Correct, correct. It will reduce the
and
complexity because
also
it is
time.
right. You are exactly right, because it is already pre-designed. So the vendor who is providing us this pre-designed component, they already have taken care of the complexity. So at our end, we can just procure it, plug it, and play it. Correct. Right? And intellectual property and types of IPs, right? Hard IP, soft IP. Hard IP is already the layout is also freezed. Soft IP means layout is not freezed. In physical design, we have flexibility to do the layout. Okay, we can choose whichever IP we are comfortable based on the schedule and requirement. Okay, semiconductor encyclopedia. Okay, now this is where like we go through the manufacturing process, right? So wafer manufacturing, oxidation, photolithography, etching process, packaging, electrical die sorting process, metal wiring process, deposition, and ion implantation process. Right? These are the 8 main steps of semiconductors process at a glance. Okay. So wafer manufacturing, what is wafer? The main material used for making semiconductor integrated circuits. Okay, so this material itself is nothing but silicon. I think we had a question, right, when we thought of parking it and discussing it here, right? So this is silicon, the one which you are seeing here in the ash color, right? I mean, this itself is silicon. Okay, the material, the main material used for making semiconductor integrated circuits. Okay, because of several advantages of silicon, we are still going with CMOS, right? In fact, FinFETs are also based out of silicon only. Okay, now oxidation, right? The process of making the foundation of a transistor by forming a silicon oxide film, SiO2, on the wafer surface. Okay, this is oxidation. This is very, very important in order to form the wafer surface. Okay. So please stop me, or I think one of you had a previous question as well on the type of material we are using. Please stop me, and we can go through that question as well, or any new questions as well. Photolithography, the process of drawing semiconductor circuits on the wafer. This is where it is. I mean, this is where your layout is taken, which you get it from the physical design, and this machinery will draw the semiconductor circuits on the wafer based on the layout, which is outcome of the physical design. Right? This is photolithography. And then etching process. Okay, the process of making patterns that form the semiconductor structure. Right? Removing parts other than the necessary circuit patterns. Exactly, your shapes are coming into picture, your transistor size, metal shapes are coming into picture. This is etching process. Okay, deposition and ion implantation. Deposition, the process of making a thin film that protects, distinguishes, and connects each circuit. Ion implantation, the process of giving electrical properties to semiconductors. Okay, oxide film, implant, thin film. Okay, so deposition and ion implantation are very, very important. Based on this only, your semiconductor properties will come into picture. Okay, so we have 3 types, right? I mean, just to go recap: conductor, insulator, semiconductor. So semiconductor properties are being put into wafer at this particular step, deposition and ion implantation. Okay. Metal wiring process. This is where your actual routing will come into picture. The process of linking the metallic wires so that electrical signals are delivered well in the semiconductor circuits. Okay, these are all the actual metals. Okay. And EDS, electrical die sorting process, the process of checking whether each chip has reached the desirable quality level through electrical property testing. Okay, we need to make sure that the die yield is as per expectation, whether the die is working as per expectation. Packaging process, the process of making parts for semiconductor chips to exchange signals externally and forming them to be safely protected from various external environments. Okay, the die, as I mentioned, we cannot directly touch it with the bare hand because the electrostatic discharge from our human hand can damage the die. So we need to have an external casing. That external casing is nothing but package, right? Where we have bond leads, right? Which will connect it to the board, soldered to the board, right? And as we do it in the engineering labs, right? I mean, we put the IC into the circuitry using these bond pads. Okay. So lowest yield, highest yield. What does it mean? Yield gradient. The chips along the edge exhibit lower yield, right? When we have the chips at the edges, right? Usually the yield will be little lesser compared to the chips which are at the middle in a wafer. Okay, because the manufacturing process is robust at the center as compared to edges. Okay, it doesn't mean the edge chips will be discarded; they will also be used, but then the yield will be slightly lesser. Okay. All right, now we have entered into physical design, which is our actual demo, right? I mean, the demo part of today. Okay. Any questions so far before we enter into physical design? Any questions on the topics discussed so far, or any inputs, any comments? All good?
Sir, I have one
It's
question.
clear,
After
sir.
1 nanometer, what they gonna implement after 1 nanometer? Because nowadays everyone working upon 2 nanometer, 3 nanometer, and uh, after 1 nanometer, what they gonna do?
It is going to be minus. So what will happen is after 1 nanometer, we will enter into minus era. So what does minus era means, right? Again, so in a layman language, right? I mean, the technology node, even though it has reached 1 nanometer, right? I mean, after 0, it will enter into negative. But then in a layman language, the transistor size will still keep reducing. So as we saw in the previous slide, right? FinFETs and CMOS are there, and then gallium arsenide is there, gallium nitride is there, silicon on insulator is there. So these experiments are going on, the R&D is going on these different materials, on these different technology types to help us move forward. Okay, because end of the day, we need the size of the transistors to be reduced as small as possible. We need to meet the Moore's law, which is nothing but double the size of the number of transistors in a chip doubles every 18 months. The Moore's law has to be followed, right? We need to meet the demands of the electronic gadgets, right? Now, for all of these, we need the size of transistors to be as small as possible. So definitely, it will not be end of the road or end of the tunnel. Okay, all the other materials, other technology types which are being experimented, which are in the R&D phase, they will pitch in, right? And they will take this journey forward. And of course, right now we are in 1.8, probably very few companies, they are into 1.2 nanometer. And by the time we completely move out of 1 nanometer, it will be anyway close to 2034 or 2035, another 9-10 years on an average, right? And it's a good amount of time because as we saw in other slides as well, how the packaging department has improvised a lot, how the memory division, embedded memory types, right? How they have improvised a lot, how SOC has improvised a lot. So every semiconductor value chain, as we saw, right? IDMs or fabless companies or fab or I would say like packaging, right? all the companies in the semiconductor value chain, they are progressing actually. And definitely it's not end of the road. So negative technology node will be there, but then it's again like distant second decade, I would say, not immediate. I mean, at least another 10 years easily it will take to close on the 1 nanometer and below technology nodes, because I mean, like we need to have less than 1 nanometer nodes as well, right? And tool cost has to be mitigated, because tool cost is kept on increasing because of advancement in technology node. Even the cost also has to be considered into progress. So multiple factors, I would say, goes into the equation of this technology node. Does it
Sir,
answer?
and I have another question. Like I have read one article that CMOS won't be useful after like 22 nanometer. After like 22 nanometer, they were using FinFET only.
No, CMOS, as I mentioned, we are still using CMOS. Okay, whether it is digital or whether it is analog, even 4 nanometer, 5 nanometer also, we are still using CMOS, not like 22 nanometer, right? But then below 4 nanometer and all, we can still use CMOS, right? But the FinFET plays a vital role compared to CMOS. The reason being, FinFET has advantage of lesser power consumption, lesser dynamic power and static power consumption, right? So that is the advantage which CMOS is not able to provide below 4 nanometer. But other than that, let's say if your target is not on the power, but if your target is on the area consumption, performance consumption, right? Then you can still go ahead with CMOS. Okay, but then since majority chips which we take up in the lower technology node, especially 3 nanometer, 2 nanometer and all, considering the cost that is associated, because cost will be very high for implementation, as I showed in some of the slides, right? EDA tool cost, physical design cost, everything will shoot up as we come down in the technology node, right? 2 nanometer, 1 nanometer and all, the cost will be high. So considering the cost, right, and the application, let's say the application is low power application. Now in low power application, even though CMOS provides lot of advantages, we still go with FinFET. The reason being our main criteria is power consumption, to reduce the power consumption, because majority devices which we are manufacturing with that high cost, right, are battery operated. And we need battery life to improve, and that's where like we go with FinFETs. But otherwise,
Due to
definitely
leakage power,
CMOS.
in CMOS there is some leakage power, right? Then that's the reason why they want to
Correct,
minimize.
correct. You are right, exactly right. So power consumption is the main criteria, dynamic power, static power, right? So that's where like we are going into FinFETs. But comfort wise, if you have to ask me, comfort wise, CMOS is much matured. I mean, you can easily simulate the CMOS and get the desired values, right, as compared to FinFET, right? But then if the technology node or the technology type which is being used in the technology node, right, if it gets improvised and CMOS also becomes very less power consumption based option, then again I think CMOS will flourish back. But still, up till 4 nanometer, we are still going ahead with CMOS, considering the pros and cons we have with this technology type.
Okay, sir. Thank you.
Okay. All right, nice, interesting questions. All right, now we are into main focus. Okay, we are into actual physical design. Okay, so all the slides which we covered till now, they were kind of introduction to understand what are electronic circuits, what are VLSI, what is the history of VLSI, LSI, MSI, right? I mean SSI, and then how transistor evolved in 1940s and where we are today. Okay, it was all a kind of background info before we can actually deep dive into physical design. Okay, now what is digital implementation or what is physical design, right? So digital implementation is a process of importing a gate level netlist as well as the technology libraries which are coming from foundry and generating a physical design that meets PPA, power, performance, and area goals. As you can see here, this is how the netlist will be. This netlist has to be mapped into layout. So we'll be going through the live EDA tools demonstration as well for Synopsys and Cadence. So we have put a snippet here where like the netlist, once it is mapped into layout, how does it look? Okay, so completely you will end up with seeing the cells and routes. All right. And this is the broader picture of the physical design flow, where we break the entire bigger design into smaller parts using a technique called partitioning. And inside that, we have physical design where we do multiple steps. Okay, floor planning, placement, CTS, routing, all those things. And finally, if everything is fine as per the PPA requirement, okay, then we go to fabrication. Or else, as per the flowchart, we keep iterating the process till the desired PPA is not met. Okay. Now this is a kind of chain, okay, from the initial design specification all the way to the design layout, what all things we go through, okay. From the specification, chip specification, we go to architectural design, okay, followed by RTL coding, okay. This is where your Verilog and VHDL will come into picture. And then we implement it into a netlist format. We test it out whether it is meeting the functionality. Then we do physical design. And inside physical design, we complete all the steps all the way from floor plan till routing, and finally the layout is sent to fabrication. Okay. Similarly, the chip specification, it goes again through verification, RTL synthesis. This is just a detailed version of the image on the left hand side. Okay. RTL synthesis, partitioning of the chip, DFT will be added so that we can understand whether the chip is working post fabrication. Then floor planning, placement, CTS, routing stage, all these 6, 7, 8, 9, these are physical design steps. Finally, we verify the layout of the physical design and send it across. This particular file, the one which we send it to fabrication, that is called as GDS2. Okay, graphical design systems. GDS means graphical design systems. All right.
How much technology do we use here?
In the labs or
Yes,
in
sir.
the industry? Is the question
In the labs.
related? Sorry, is it in the labs?
Yes, sir.
In the labs, it is 32 nanometer. So that's the industry standard which EDA tools provide, and probably few projects, right? I mean, sometimes the EDA vendors also provide us with 28 nanometer, but roughly I would say 32 nanometer is the technology node which the EDA tool vendors will provide for the courses.
Okay, sir.
Okay. All right. Now coming back to overall flow, right? I mean the same which we discussed in the previous slide: system specification, architectural design, RTL design and verification, synthesis. This is where the physical design will come. And inside physical design, we have placement and routing and sign off. So placement and routing, again, it incorporates partitioning, floor planning, placement, as we can see, placement of standard cells, floor plan, as we can see, placement of macros, and clock tree synthesis, where we provide clock buffers and inverters in order to reduce the load of the clock tree, and then finally routing. And these are the different sign-off checks, right? Because we need to make sure that the layout that is generated in the physical design is proper to send it to next steps. Okay, so we do the parasitic extraction where R and C are extracted, then physical verification where we need to make sure that the layout is ready for fabrication, followed by equivalence check where we need to make sure that while the design is going through several stages, all the way from specification, there is no change in the functionality. Okay, the EDA tools which are being used at every phase of the flow, they are not modifying the functionality. So that's where to catch that we have formal verification, and similarly to make sure that performance we are not compromising, we need to do the static timing analysis. Similarly, we need to make sure that every cell in the layout is getting the needed power, and we are ensuring that using the power analysis IR drop. Okay, this is how different sign-off checks are done before we send the layout of physical design to mask preparation. So in a nutshell, physical design takes the netlist from synthesis and maps it into layout, which can be sent for mask preparation. Right now, for mask preparation, we send the layout to fabrication, where in the wafer the die is manufactured, and post that we do packaging, and that packaged chip has to be tested before we release it into market. Okay, only the tested chips will be released into market. Okay, so this is the overall a bigger picture, I would say. of the specification till the finished chip. Okay, and how the physical design is positioned in this bigger picture. All right, any questions here on this particular slide? Anybody, any questions? I can pause here for a minute or two to take up any questions. Is it clear, everyone?
Sir, after placement, while doing CTS,
Mhm.
if standard cells are removed, what may be the reason, sir?
We don't remove the standard cells in the CTS. Okay,
I
so
mean,
in
while
this,
doing CTS, if I have worked on Cadence Innovers,
okay,
we had done a project on MBIST. So while doing that, we done placements. After that, the standards after doing CTS, all standard cells get removed, sir. What may be the reasons?
no, it won't get removed. I'm not sure what happened exactly in your project, but ideally, in an industry standard flow, the standard cells will not be removed. So once we place the cells in the placement stage, once they are legalized, we don't remove any kind of standard cells. They continue as it is. In fact, in the CTS, we add the cells. So we add clock buffers, we add clock inverter pairs in order to meet the CTS requirement, but nowhere we remove the existing cells. And in the routing stage, we do connections to these cells, inputs and outputs. Did I answer your question?
Okay, sir. Okay. Actually, while doing optimizations after CTS, I guess in somehow standard cells got removed.
Okay,
So
probably the optimization options which might have been given, right? It might have replaced, let's say, low drive strength buffer with high drive strength buffer, or it might have replaced a buffer with inverter pair. But ideally, the functionality has to be remained same. Okay, it might have done some restructuring, that's all, in order to optimize the netlist as per the criteria provided.
okay, sir.
All right. Okay. Thank you. Nice question. Yeah. All right. Let's go to physical design course content. Okay. I would like to spend a few minutes here. Okay. I'd like to spend a few minutes so that we can show you the content. So course highlights, let me go through quickly the course highlights. Already this has been covered in the initial Semicon slides, but then I felt, I mean, let's recap again in case you have any questions or any inputs as well. Okay, so we have 1,000+ mock interview questions and answers to prepare you extremely well for the interviews. Okay, because all these are with answers, questions along with answers, and these are all the interview based questions, not the academic, real-time interview based questions. Okay, and similarly 18+ instructor team led training. Okay, so instructor team led training means we have a team who will work with us for conducting the classes as well as labs and weekly exams. Okay, stop me if you have any doubts or any questions. Okay, and which learning content. So lot of learning content is there for every topic or every module that we are planning to provide as part of this demo or as part of this course. Okay, Synopsys or Cadence EDA tools. Okay, we'll be using either one of these tools, either Synopsys tools or Cadence tools. Okay, and weekly assignment test. So every week Saturday we'll have weekly assignment test in order to understand and course correct if you are lagging in the concepts or if we are going too fast and how we can correct ourselves. Okay, so weekly assignment test will give us an opportunity to understand how the course is going and to extra focus on couple of topics, right, as per the requirement based on the results of weekly assignment tests. Okay, and every week Sunday we have free YouTube live presentation from Semicon Technolabs where you all can participate in order to gain the technical knowledge. Okay, on different multiple topics. All right. Any questions on the course highlights? Anybody? All clear on the course highlights?
So we'll get 24 hours access to tools, right?
No, it is not 24 hours. So in the working hours, we'll have the tool access. Okay. So I will be coming to the EDA tools part where I will be explaining on the EDA tools which we are providing and what are the timings, right? We are going through. Okay. So it's all covered in the working hours as well. Any questions on the course highlights? If no, then I will go to eligibility criteria. Of course, this again has been covered in the Semicon slides. Okay, we are looking at like at least 60% throughout academics, right? ME, MTech in VLSI or embedded systems or digital electronics, and BE, BTech in ECE or EEE. Okay, these are relevant fields, I would say. Okay, and easy to understand the VLSI syllabus as well. Okay, course duration is complete 4 months. Okay, and then EDA tools, right? I mean, these are the EDA tools which we are planning for this batch. Okay, so design compiler or genus, right? For logic and physical aware synthesis, IC compiler 2 or fusion compiler or Innovus, any of these tools for physical design, star RC for RC parasitic extraction, prime time for ST and EC host, ICV for physical verification, DRC LVS antenna. Okay, and we have marked to some of the tools which are non-PNR tools. Okay, they have been marked as star. Star marked tools are additional tools where overview is provided for students to have exposure. Main focus will be on PD tools. What are PD tools? IC compiler 2, fusion compiler, Innovus. These are the PD tools. So main focus in the 4 months will be on these tools. Okay, this is where, because this is mainly physical design course, but at the end you will also have exposure on synthesis tools, parasitic extraction, ST and ECOs, physical verification. Okay, and working hours, Monday to Friday 9 a.m. to 6:30 p.m. Right, these are the working hours. Accordingly, the classes and labs will be organized. Okay, and Saturday 9 a.m. to 5 p.m. Okay, this is how the working hours are. You will have tool access during these working hours. Okay, and institute will remain closed on Sundays and all public holidays. Okay, syllabus. So we have different modules. Okay, 10 modules are there, and in every module, clearly we have given the syllabus, which all will be covered, module related syllabus. Okay, and duration by when it will be covered. Okay, in the first week, all these 4 modules will be covered. Okay, please go through this one, right? And in the second week, we'll be going through module 5 to 6. Please note that these are all overview. Okay, we don't have to go deep dive into this. Our main focus will be physical design, where we go deep dive. Okay, so this is where we'll be spending majority of our time. Okay, and then finally, we'll also be working on mock interviews, cover letter and resume preparation, interview guidance, soft skills training. Okay, and of course, practical lab work will be there, flow automation, AI and ML, and runtime reduction. Okay, so the PD course is designed to cover PD deep dive along with overview of synthesis, partial DFT with scan. It's only partial, right, with scan insertion, right? We are not covering other parts of the DFT, right? Only the one which is related to physical design will be covering, and 5 different sign-off checks. This will extensively help to open up wide VLSI job opportunities for students as their domains expertise will be vast. Okay, so along with PD, we are giving overview of all the other things as well to help increase the scope of job opportunities. Okay, at the end of the PD course, we experienced to handle designs for both RTL to GDS2 and netlist to JDS2. Okay, gain hands-on experience in using EDA tools, have thorough understanding of full ASIC or SOC implementation flow steps. Okay, geared up in below different domains: synthesis, DFT for scan insertion and stitching, physical design deep dive for handling chip and blocks, sign-off checks with respect to physical verification, DRC, LBS antenna, ST and ECOs, EMIR, LEC formal verification, UPF and CPF low power intent, flow automation using scripting, right? Tcl, Perl, Python, Shell, and Unix. We'll be giving overview of all these scripting languages along with GVim. Okay. Equipped with 1,000+ mark interview, real-time interview questions and answers, which will be actually asked in your interview. Okay. I would say if you can prepare this properly, okay, at least like 3 to 4 years of experience range interview questions and answers will be easily covered in this mock interviews. Okay. Then cover letter preparation, resume, and soft skills. Okay. Any questions on the course content? Everything has been very clearly put in the website, which we will be strictly following, right? So that you gain the maximum advantage by enrolling in the PD course. Any questions? Is it clear?
Sir, how much this institute is charging for 4 months?
So Taslim will connect. You can connect with Taslim as we shared the mobile number and email ID. So you can connect with Taslim and get more details on it.
Okay, sir.
Okay. Any other questions? Anything on the course content, course highlights, eligibility criteria, course duration, EDA tools, working hours?
Sir, morning section, they're gonna take classes like from 9 to how many hours like per day classes?
So usually it will be right. We'll be publishing the clear-cut calendar invites. Okay. So 9 to 6:30, right? In this, either we can go with 9 to 1 or we can go initially with complete classes as well till we get an understanding on the physical design. So we'll send out the calendar invites accordingly once the batch starts. But the working hours will be 9 a.m. to 6:30 p.m. You can stay more as well. Office will be open. If you are interested, you can stay more, and any of you can stay more and then practice the labs or practice the, go through the theory part as well. Okay, that's absolutely fine for us.
Okay, sir.
But regular working hours will be 9 a.m. to 6:30 p.m. That's the standard working hours. You can come little early as well if it is convenient for you, or you can stay late as well. Okay, till up to maybe 7:30 or 8 o'clock.
Okay, sir. Thank you, sir.
All right. Yeah. Thank you so much. I think we are clear. Okay. So let me go back to presentation. Okay. All right. Now we have reached the actual EDA tools practice. Okay. Let me share the screen. So this project is ARCA top. ARCA means Optimized Reconfigurable Cell Array. It is a reference project given by Synopsys for implementing physical design using Synopsys tools. Okay, the ARCA is part of RISC processor, Reduced Instruction Set Computer. Somebody mentioned they have done RISC processor related project in third year, right? So this ARCA top is related to RISC processor. All right. So let me share the screen and then present you the tools. Okay. So this is how the tool looks like, actual tool looks like, okay, in the physical design world. All right. So as you can see here, can someone confirm the tool is visible? Any
Yes,
of
sir.
you? It is visible, right? So this is the real tool, right? Which we are showing where like you'll be practicing these tools in the course. Okay, so this is the ARCA top from Synopsys given by Synopsys. Okay, this is how the physical design looks like. All right, now the ones which you are seeing here, okay, the blue color ones, right? The bigger ones are these blue color ones. These are called as macros. Okay, where I am moving my cursor. Okay, these are called as macros. And the ones which you are seeing here, the pink color ones, okay, the pink color ones All right. So these are nothing but your standard cells, the pink color ones. Now, in a design, when we saw the digital implementation slide, in a design, we have netlist. The netlist is mapped into layout, right? I mean, that's what we went through in the slides in the digital implementation or in the physical design. Now, when the netlist is given to us as input, which is our first input, we will be having the standard cells, which you can see here in the pink color. We'll also be having the macros, which you can see here. Okay. So these standard cells and the macros, which are coming from the netlist, they have to be placed properly as per the connectivity defined in the netlist. So as per the connectivity, we are clearly placing them here. Okay, this is nothing but in the placement stage. Okay, we place all the macros and standard cells. Okay, and once we place all the macros and standard cells, as we saw in the previous slides, we will do clock tree synthesis where we are adding clock buffers and clock inverter pairs to build the CTS, followed by routing. Okay, so this is how the Arca top looks like. All right, now let me show you DTMF. Okay. So this is the schematic actually. Okay. So Genus is a synthesis tool actually. So this is how the schematic is. And let me show you Innovus. Okay. This is how the Innovus tool, which is from Cadence. Okay. In Innovus, we have DTMF. So in DTMF, we have this particular full chip level project where these are called as IO pads. These are all IO pads. Okay. These are macros. Okay. This is PG mesh. This is actually the PG mesh. All right. These are IO pins connected to IO pads. These are corner IO pads. All right. Okay. And these are the key ports. The dark orange color, right, or ash brick color. So this particular one are called as key port margins. Okay. And between this um, blue color and this IO pad, whatever the gap we have, right, this is nothing but your core to die area. Okay, this is nothing but your core to die area, this distance, this particular distance. Okay, this particular one from here to here. Okay, this is how your core to die distance will be. And this is your key port margin. Okay, and these are your different metal layers. Okay, so different metal layers are used, and these are your rings actually. Okay, these are your rings where you can exactly you can draw the ring. The advantage of power ring is directly you can connect the stripes to the power ring. Okay, that's the advantage. All right. Now let's say for example you have the IO pads, right? And to begin with, all these IO pads will be sitting outside. You need to get these IO pads to arrange in this fashion. Okay, which you do it in the floor plan stage, followed by placing the macros inside, right? I believe the one somebody did physical design using Innovus, right? So I mean he can correlate this one, right? In the floor plan stage, we are placing all the IO pads and then macros as well inside, and in the placement stage, we are getting the standard cells to be placed in the gaps wherever the macros are not placed. Okay, and this PG mesh is done in between the floor plan and placement. Okay, this is where we do the PG mesh. All right. And for starting the physical design, we get the netlist from this particular tool. Okay. So this is called as Genus. Okay. And this is the DTMF overall netlist. Using this netlist only, we do the physical implementation. So this particular netlist, right? I mean, it has, okay, 1, 3, 7, 8, 3 leaf cells and 4 blocks. Okay. So clearly, I mean, how many modules, standard cells, nets, and terms are there? Okay. And this is how the physical aware synthesis looks like. The tool, how it shows the physical aware. Okay. This physical aware information, finally, it gets mapped into something like this. Okay. This is what we do in the physical design. Okay. Of course, we have to do routing followed by sign-off checks. Only then we can tell that our layout is perfect and we can take it forward. Okay. All right. So this is how it looks like. Okay. So Arca top, right? The one which we saw, Arca top, right? And then we have DTMF. So DTMF is a cadence project. DTMF full form is dual tone multi-frequency. DTMF is a technology used with touch tone phones. Okay, best known to users as the sound made when pressing a number key. It signals the phone company that you want to make a call and sends a command to the switch. DTMF is a reference project for implementing PD using cadence tools. Okay, you remember, I mean, like previously or even today, right? I mean, some of the phones, when you um, press the keys of the phone, okay, from the keypad, you will hear the sound. Okay, that is because of internal DTMF logic. Okay, and this logic signals the phone company, right, that you want to make a call and sends a command to the switch. Okay, so this project is done using cadence tools. Okay, and this is how the routed design looks like. I showed you the placement stage design, and then this is how the routed design looks like. Okay, completely routed design where you can see all the connections have been done as per the netlist given as input to the physical design. Okay. Any questions so far on the EDA tools, Synopsys EDA tools and Cadence EDA tools? Anybody, any questions? Is it matching? I mean, the project which you guys did in Innovus, was it DTMF or any other project? Was the project Innovus? Is it clear, everyone? Any questions?
Sir, I was having a question like related to the
Yeah.
department. I'm from the electrical background.
Mhm.
Yeah, and these are completely like most of it from the electronics, right? In this,
Mhm.
like, is there any like problem for us if we take this course and we may not understand or it may be difficult?
No, triple E, right?
Yes, yes.
Yeah, triple E should not be a problem.
Okay.
Okay. So that's where in the triple E, right, to cover the triple E as well. So we have given overview of combinational circuits, sequential circuits to the extent which is needed for physical design. Similarly, overview of CMOS, FinFET technology nodes, fabrication process, right? So whatever is needed to start the physical design, we are completely providing the overview so that you have that background, you have that foundation built up, which can help you to take up the physical design course. So that's where, like in the section 6, we are starting the physical design, right? So till section 6, all the other sections like section 1, 2, 3, 4, 5, this is only to refresh the concepts if you are already from ECE background, or to help other domain engineers as well to form a foundation, and from there you can start looking into physical design deep dive. So all these 1 to 5 sections will help us to form that foundation.
Okay, sir.
Okay.